Welcome back to another fun and exciting Q&A episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
I am your temporary host this episode, filling in for your beloved Andrew Dunkley, and my name is Heidi Campo. And joining us today to answer all of your burning questions is the lovely Professor Fred Watson, astronomer at large. Hi, Fred. How are you doing?
But well, Heidi, thanks, and great to see you again. I'm so happy that we have these conversations because it brings a new excitement to the whole idea of Space Nuts with your questions as well as mine.
Absolutely. And I know you're going to have so much fun at your conference this week. Speaking of questions, you're going to probably be answering a lot of questions and giving a lot of questions yourself. Is there any talks you're really looking forward to?
Oh, yes, there is actually. There's one day tomorrow, and this is an afternoon when the people who are most directly involved with some of the projects that are going on in Australian astronomy, they get a chance to give an update. And it's things like what's happening with the Square Kilometre Array Observatory, which is being built jointly in South Africa and in Australia. It's things like, well, the Vera Rubin Observatory that we've talked about already. We've got connections with that. All of those things, these are sort of almost like news reports from these various facilities. And there's a lot of big questions that we need to ask in Australia about where we go with for example, our membership of some of the international observatory communities. So that's the one that's going to be the highlight for me. That will be tomorrow afternoon, and I'll report back, no doubt, in our next issue of Space Notes.
Oh, I can't wait to hear it. That sounds wonderful. Well, Lay, let's go ahead and just jump right on into our questions then. We have, it's kind of typical fashion. We have a couple written questions and we have a couple audio questions. And so I'm going to go ahead and read. And I did not say so because our next question's from Minnesota. It just came out that way. But our next question is going to be a written question. And this is from Greg from Minnesota. And Greg says, "G'day, Space Nuts. I'm Greg from Minnesota, and I have two questions for you this week. One, what, if anything, is being done about Kessler Syndrome? Are there any plans to test something to remove space debris? Question two, why is Venus's atmosphere so thick? CO2 is more dense than N2 and O2 in our atmosphere, but I've heard that even if you removed the CO2 from Venus's atmosphere, it would still be 3 times more dense. How can it hold such a thick atmosphere? Or is it the Earth that is the odd duck that has an unusually thin atmosphere for a planet our size?"
They're great questions from Greg. I'm going to do the easy one first, which is what's being done about the Kessler Syndrome. Well, the Kessler Syndrome, I'm sure most of our listeners know, is that it's the potential for there being a kind of runaway collision process among orbital debris, things that orbit the Earth, particularly in low Earth orbit, which is getting very, very crowded. At the moment, there are 30,000 pieces of debris that are being tracked, and they're bigger than about 100 millimeters across. But there are millions of smaller bits. And remember that everything's going around at 8 kilometers per second or thereabouts. So it is potentially a very dangerous thing. If you got a big enough collision between two defunct rocket bodies, then the debris from that could have this sort of domino effect in basically filling space with debris. That's the Kessler Syndrome. And what's being done about it is, yes, the recognition that we do need to fix this because Earth orbit is becoming more and more crowded. There is, as time goes on and the more spacecraft that we launch, and there are something like 12,000 active spacecraft in orbit at the moment, as the numbers increase, the risks increase that you will eventually have a Kessler Syndrome phenomenon. And then it's too late. You've got space that's actually unusable. which is a horrible thought when we think of how much we need space and how much we use the facilities that come to us because of orbiting spacecraft. So there is, in a regulatory sense, there is now the need. You have to show whenever you launch a spacecraft that it's going to be deorbitable. In other words, there's got to be a way of clearing it from low Earth orbit. Plus, there are missions being planned to actually remove some of the larger pieces of space junk by decelerating them so that they burn up in the Earth's atmosphere. So a lot is happening, but it's a slow process, and it's actually quite a difficult job. Moving on to Greg's second question, which has got my brain in a panic, because I'm going to front up here and say I don't actually understand this, but I'm not a chemist. So let me just tell you what the story is. As Greg says, well, why is it Venus's atmosphere so thick? That's the easy part, because we have an atmosphere that is something like 96% carbon dioxide. Whereas, the carbon dioxide in Earth's atmosphere is measured in parts per million. It's much, much lower than that. So, as he says, CO2 is more dense than nitrogen and oxygen in our atmosphere. But I've heard that even if you removed the CO2 from Venus's atmosphere, it would still be 3 times more dense. How can it hold on to such a thick atmosphere? And I think you're right, Greg. All the stuff I've read about the atmosphere of Venus, and I've churned through this quite a bit recently, it implies exactly what you've said, that if you took away the carbon dioxide, what you'd be left with would be essentially a nitrogen atmosphere, which is not that different from Earth's, because we have a nitrogen atmosphere which has some oxygen there. I can't remember. It's the exact percentage, something like 15%, I think, oxygen. And so you've got an atmosphere that does look more like Earth's, but is still going to have 3 times the atmospheric pressure of Earth. And I have struggled to work out why that is. I think it's probably due to differences between the planets themselves. They are very similar in size. In fact, Earth is slightly more massive than Venus. But there may be issues to do with, for example, the internal structure of these 2 planets that makes them different in terms of what their atmosphere would do. So it's a piece of work that I'm going to continue researching, Greg. Thank you for pointing me in this direction, because it's one that is intriguing me and annoying me, that I can't immediately see the answer, the simple answer to your question. There may not be one. It might be far more complex than we're currently expecting. But we will keep on with this and no doubt talk about it again down the track.
Thank you so much, Greg. Our next question is from our favorite father-son duo from Portugal, and this is an audio question. So I'm going to give Fred a second to cue that up, and we are going to play that question for you right now. You guys are going to be able to listen to their question, and then Fred is going to answer it. So here we go.
Hello again. This is Philip, Henrique's father, from Portugal. I just got home from work. It's 9:30 in the evening here in Portugal. And Henrique was awake, eagerly waiting for me to get back home because he wants to ask you another question instead of being asleep. Thank you so much for answering his questions. He really loves it when you answer his questions. And he asked me to listen to your podcast every time it's available, another episode. I just wanted to say thank you for entertaining his questions, and I'll leave him to it.
Hi again. I have another question for you about stars and black holes. How can black hole stars support the mass of the black hole in there or without collapsing? And can you please tell more about them, like do they can support planets, and how are they created, etc. Thank you for answering my questions. Bye.
This kid's going to be the next Einstein.
I think so too. Yeah. So thanks to Philippe for letting Enrique stay up late enough to record a question for Space Notes, and they're great questions too. I think, as I understand it, Enrique, your question was, how can a star, basically what stops a star from turning into a black hole? How can a star be supported? And the answer is, it's all about the physics of the way stars work. Even stars like the sun, which is relatively modest in size, certainly isn't going to cause a black hole to be formed when it dies finally in perhaps 3-4 billion years' time. But a star like the sun is a balance between the gravity that wants to pull everything to the middle. It's a blob of gas, and gravity basically wants everything to sink to the middle. And if that was the case, then it would turn into something not quite like a black hole. It would turn into a white dwarf star, which is similar to a black hole, but not quite as compact. But what stops that, as the star is in its normal lifetime, is the radiation that is being generated by the nuclear processes, basically the atoms being smashed together in the star's center. So there's all this activity generating energy in the center of the star as radiation. That radiation pressure, which is acting outwards, balances the gravity exactly. So it's a delicate balancing act where the gravity is the tendency of the star to collapse is actually inhibited or stopped by the radiation pressure coming from the nuclear reaction. So that's what happens in a giant star, perhaps 10 times bigger than the sun. During its lifetime, most of its lifetime, that balancing act is keeping going. The outward pressure is stopping the gravitational collapse. But these massive stars burn up their hydrogen, which is the fuel that generates these reactions in the center. They burn the hydrogen up very quickly. And once that hydrogen has gone, then you basically, it's not quite as simple as this, but basically the energy switches off. So there's nothing to stop the star from collapsing. It simply collapses under its own gravity. And a star that's big enough will indeed collapse into a black hole. Slightly smaller stars collapse into something we call a neutron star, which is where the subatomic particles are all crowded together. Then a slightly smaller star than that will collapse, like our sun will, into a white dwarf star, which is where all the electrons are bunched together. Neutron stars, and I'm just moving now to the second part of your question. At least one neutron star we know does have planets, and that is it's one of the first planets beyond the solar system that was discovered, because we could see its effect on the neutron star. And so it is possible for a planet to survive that explosive ending of the star that results in the core collapsing. And, quite often the outer layers are blown away as well, because that collapse is very explosive. It sounds weird that something collapsing should cause an explosion, but that's what happens. So I hope that covers the etc. in your question, Enrique. But that's basically what we know about the way black holes form and about the way planets might survive being around a black hole. We don't know of any planets yet that are around black holes, but we do know that they're around neutron stars, which are not too different from a black hole.
That's fantastic. Yeah, please keep the curiosity going. Feed that kid whatever science he needs to keep fueling these questions, because this is really, really fun.
Let's take a breather from the show for a moment to tell you about our sponsor. If you're travelling soon, like I am at the moment, and you're tired of paying ridiculous roaming fees, say hello to Saily, S-A-I-L-Y. It's the easiest way to stay connected abroad with just a few taps. Now, Saily is an eSIM app that gives you fast, secure and affordable mobile data in over 190 countries. There's no physical SIM. You don't have to pop yours out and put another one in. No surprise charges. You just download, install and connect all from your phone. It's very secure, very easy to use. Your privacy is also locked down. You can enjoy the benefits of ad blocking, virtual location, secure browsing, and that's all free with every plan on Saily. Now, whether you're working remotely, streaming on the go, or just posting beach pics, Saily has you covered. And here's the deal. Go to saily.com/spacenuts and use the code spacenuts for an exclusive discount on your first plan. That's saily.com/spacenuts and use the code word spacenuts. You won't regret it. It works really, really well. It's fast, it's efficient, it's secure. That's saily.com/spacenuts. Now back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Next question. There is no way I am going to read this. There are a couple pages of math equations on it, and I would put you guys to sleep if I read all of these numbers in a row. But I am going to paraphrase. So our next question is from, I hope I'm saying your name correctly, Eastalk. And I looked it up. It looks like that's a Slovenian name. So I'm wondering if you are from Slovenia or not. I love Slovenia. Beautiful, beautiful country. But Eastalk says, the other day, let's see if I can even read the question, if I paraphrase it. The other day, you discussed the density of black holes. And then he goes on to say that he looked up an AI formula to compare the density of a proton with the density of a black hole. And he's trying to calculate the density using, for each, using a formula. And then he goes on and on and on with these formulas. And then for a black hole, we'll consider a Schwarzschild black hole, which is the simplest type of black hole. The density of a black hole depends on its mass. Let's take this example, more equations, and he is basically just asking if the density of a black hole is significantly higher than that of a proton. This comparison illustrates the extreme compactness of black holes, where a large mass is compressed into a very small volume, leading to incredibly high densities. Fred, you've got this math thesis in front of you, so you you can break it down for us.
No, you've summarized it perfectly, Heidi. And so yes, so what we do is look at so density is mass over volume, and that's a simple calculation, and we can do it. I mean, in school physics, you do it for lumps of wood or things like that to work out what the volume is and what the mass is, and then you get the density. It's a little bit different when you're looking at subatomic particles like a proton, but you can do the same sort of calculations. And yes, so the AI that Eastalk relied on, I think got the density of a proton approximately correct at 6.73 times 10 to the power 17 kilograms per cubic meter. It's very dense, a proton. But then the calculation goes on to estimate the density of a black hole, and actually comes out with the not surprising result that the black hole is more dense than the proton, about with a ratio of I think it's more than 100, actually, more than 100 times. The only thing is, I think that the AI might have misled you there, Eastalk, because what the AI has done is taken, as Heidi mentioned, it's the Schwarzschild radius, which is the radius of the event horizon. And that's not the radius of the black hole. AI might think it is, but it's not, because the radius of a black hole is 0 by definition. And that means its density, because mass over volume, it's the mass, which does have a parameter, over the volume, which is effectively 0. That gives you basically an infinite density. And that's one definition of a black hole, is a point in space where the density is infinite. Now, we don't know whether real black holes have infinite density, but they are probably, enough of significantly more dense than any of the densities that we might calculate for example, subatomic particles like protons. So I think the AI might have made a slight error there, but the answer is the same. The density of a black hole is very, very high indeed, and may be infinite. So a really interesting piece of research by you, Eastalk. Well done on doing that, and thank you for sending it to us to see your calculations. It's nice to see some mathematics appearing in our questions there.
Yeah, quite a few mathematics. It was very fun.
3, 2, 1.
Space nuts.
Our last question of the day is an audio question, and I don't think you mentioned your name in this question, but this is another great question that we are going to let Fred queue up and listen to, and we're going to play this question for all y'all now.
Space is huge and getting much, much bigger. Is it possible that at the beginning of the Big Bang or soon after, the microbes that made up life was generated and therefore this was spread across the universe over time? Thank you.
I do love the birds.
Yeah, the birds are wonderful. I think that's an Australian accent, I think, and I think they're Australian birds in the background. So I'm sorry that we don't know who that was from, but thank you very much for the question. And it's interesting. I mean, one of the ideas that was certainly kind of popular towards the end of the last century, in the 1970s, 80s, 90s, was that it was what we call the panspermia hypothesis, that life is common in space and gets to planets like our own by coming from space, either hitching a ride. So microbes either hitching a ride on a meteorite or something of that sort that lands on the Earth, or even actually just filtering down through the atmosphere. There was one of the great names in British astronomy, in fact global astronomy, Professor Sir Fred Hoyle. He was a very, very gifted scientist who made his mark in the years following the Second World War. But towards the end of his life, he espoused this idea of panspermia, that basically living organisms drift through space and wind up on planets because of that. But it's a very unpopular idea because of the physics that are involved. So what you need is the raw materials for life to come together in the vacuum of space. Well, space is not a vacuum. We know in interstellar clouds there are significant numbers of chemicals, and in fact we do know that the building blocks of life, such as amino acids and things of that sort, are actually present in some of these clouds of gas and dust. But for the process of chemistry to give rise to the processes of biology, you need conditions which we think only occur on planets where there's gravitational binding. You need to form membranes to basically be the walls of cells, so that when you produce a single-celled living organism, it's not just a bunch of atoms that leak out into its surroundings. It's actually held there. So you need lipids and things of that sort. Quite complex procedures. Now, in a sense, though, our anonymous questioner is right, because in the aftermath of the Big Bang, microbes were certainly not around then, because the conditions, temperature and pressures were far too high for any molecules at all to exist. Molecules would have been shredded apart, let alone living organisms. So microbes did not come about as part of the Big Bang. But the raw materials did. The hydrogen and helium, which were created in the Big Bang, that was spread throughout the universe. And what happened next was the formation of stars by hydrogen clouds collapsing under their own weight and switching on the processes that generate the nuclear fusion that actually causes star to shine. Not only do they generate energy, which we're feeling right now from the sun, they also create new elements. And it's those new elements, the oxygen, the carbon, the hydrogen, the nitrogen, all of those things are the raw materials of life. And so the raw materials of microbes were produced not initially in the Big Bang, but everything was there that we needed later on. And so it is possible that if you have microbial life, and it may only occur on planets, but planets are everywhere in the universe, it's the raw ingredients are there everywhere in the universe. And so, yes, maybe there are microbes everywhere in the universe. Whether they come to us from space, that's a different matter. But certainly, in the sense that our questioner has asked, it's everywhere. It's because the raw materials were spread throughout the universe, life could probably exist anywhere in the universe. The only issue is we haven't found it yet. And that's the rather annoying part of this whole matter. So let's keep working on that, looking for first signs of life beyond Earth.
Yeah, if you guys are hooked on math still, you can look up the Drake equation. That's a fun little deep dive you can go on to. But I just love that this question was about life in the background of it. I'm still fixated on the birds for whatever reason, but it sounded like he was coming from some kind of like conservatory or a jungle, and it was just so rich in life. Like I feel like I was in some kind of like a greenhouse with like, bugs and butterflies and insects and birds all around me. It's very cool. And you know what? At the end of the day, this planet rocks. I really, really like our planet.
Yes,
Space is fantastic, but when you really kind of you take your eyes away from the stars and you look at what we've got going on here, it's like, wow, this is pretty nice. We've got a really good looking planet here. And it really is incredible to think it's like everything that's out there. There's no planet like Earth. We really are on such a beautiful, special planet.
We are. And that's a very important point because most of us simply take it for granted and don't really think about life beyond Earth or space. I mean, when you ask people in the street, they don't realize that the Earth could be unique. It is so precious because it's actually got exactly the right ingredients for the kind of life forms that we are, and we've evolved from that. We're products of our environment.
Yeah, and then we produce all sorts of things with this gift of life, including podcasts. It's just the human ingenuity never stops. But yeah, that is it for the questions for today's episode, guys. You're fantastic. Please keep sending in your amazing questions. I love to hear them. Fred loves to answer them, and
oh no,
and it's always such a pleasure.
And as it is for me, you're quite right, Heidi. I love getting these questions. They challenge my brain, which is a good thing to have.
Yeah, well, I'm sure you're going to have a lot of questions. Fred, it's a Sunday night for me, so I'm winding down. I think my husband's making tuna steaks tonight, and then Fred is ramping up on a Monday morning, heading off to your conferences. I can't wait to hear how these go. They sound like it's going to be a very fun time for you.
I'll be sure to fill you in on everything that goes on. Thanks, Heidi. Good to talk and speak again soon.
All right, take care, Fred. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.